Jai Hind students. So this is our third lecture of our complex lecture series, and the topic for today's lecture is journey from a latch to flip-flop. So we'll be covering the basics of the latching operation and how that latching operation finally translates into a flip-flop. So these are the contents of today's lecture: basics of latching operation, then the basic latch structure, then NAND-based latch, then S bar, R bar latch, then SR latch, then how that SR latch becomes an SR flip flop, and then finally how that SR issue of invalid output is resolved by JK flip flop. So these are the contents of today's lecture. So let's start with the basic latching operation. So by latching means that we are going to latch one bit. That means we are going to store one bit. So let's say when you are sitting in a room and the room is latched from inside or outside, that means no one can enter that room further and no one can exit from that room till the time the room is latched. Once the latch is open, the state of the room can change. So this same holds true for this latching operation here as well. That means that if a 1 is to be stored or a 0 is to be stored, I'll be using a structure which will be using a 1, which will be storing a 1 as per my requirement or a 0 as per my requirement. But to start with, how this latching is happening, we can start with a basic circuit which is having two NOT gates. We all are aware that how a NOT gate works. That means this basic latching operation. That means a NOT gate is there. Okay. If a 0 is there, then the NOT gate will give 1 output. Similarly, another NOT gate is there. And if these two NOT gates are cross coupled, that means output of one NOT gate is connected as input to the other NOT gate, and similarly for the other NOT gate, the output of the second NOT gate is fed as input to the first NOT gate. Okay. So in that case, if we see that if I apply a 0, I can't apply any input, but I can assume that if the output is 1 here, then this 1 will be reaching here, and corresponding to that 1 input to the second NOT gate, output will be 0 here. This 0 will reach here, and again for corresponding to that 0, there will be 1. Corresponding to that this 1, there will be this 1 will reach here, and corresponding to this 1, there will be 0 at the output, and this 0 again will reach at the input, and this process will continue. And we can see that these 0 and 1 placements at the input and output terminals are not changing at all. So we can say that a cross coupled inverter, a pair of inverters, or we can say a pair of cross coupled inverters can act like a latch. That means can latch 0 or can latch 1. Okay. So this is a basic latching operation. How a pair of cross-coupled inverters can latch one bit of information. Okay. So this is the basic latch and the latching operation. Now NAND based latch. Okay, so let's proceed to the NAND based latch. And before proceeding to the NAND based latch, you just have to be aware that this NAND gate, how this NOT gate is going to be realized using a NAND gate. So this is a NAND gate. Okay, this is a NAND gate. And if I want to convert this NAND gate into a NOT gate, then I have to connect or short both its inputs. In that case, if I apply A here, then on both the terminals there will be A, and here it will be A into A complement, which is ultimately equivalent to A bar. So for A, I am getting A bar as the output. That means this NAND is acting like a NOT gate or an inverter. So using this concept, now I am going to design the same latch using a NAND gate. Okay, so let's draw a NAND based latch. So the NAND based latch will be something like this. Okay, so this is a NAND based latch, which will be acting exactly similar to the cross coupled inverters, because actually these NAND gates are acting like NOT gates. So that same principle will hold true here as well. But the thing is, there is no provision to latch as per my requirements. Okay. So if I can't latch as per my requirement, there is no purpose actually for this latching operation. So I have to include some provision by which I can latch as per my requirement. That means if I want to latch a 0, I should have that provision. If I want to latch a 1, I should have that provision. Okay. So how it can be done? I am simply opening the second input of the NAND gate. This structure will remain same. Cross coupling is identical, but I have opened these two bits. Okay. And now let's say I am naming them as A, B latch. So A and B are the two inputs for me, by which I can apply the inputs and see if I apply 0, 0, what is latch in the circuit, if I apply 0, 1, what is latch in the circuit, and so on. So let's prepare a truth table for this latch. So this A, B is there, and the output Qn plus 1. So what is this Qn plus 1? Next output. Okay. So we do not get confused with, the current output and the next output. So I am using Qn plus 1, and Qn plus 1 will be treated as the previous output. So either you can take previous and present, or you can take present and next. Okay. So there are output of two stages, first stage and second stage, which is either previous or present or next. So there are four possibilities of these AB: 0, 0, 0, 1, 1, 0, and 1, 1. So for 0, 0, let's say if I apply a 0 here and a 0 here. So in a NAND gate, what is the truth table of NAND gate? You can refer from here. I am writing it roughly here. 0, 0, 0, 1, 1, 0, 1, 1. So NAND gate table says that if any of the input is low, the output will be high. That means to get a high output, at least one of the inputs should be 0. So we can see that here is a 0, so output will be 1. Again, here is a 0, output will be 1. So this one will go like a feedback for this gate, and this one will reach here. But again, at 0, 1, output will again be 1. And again, at this 0, 1, output will be 1. So we can see that the state of the circuit is not changing, but the thing is, these Q and Q bar are not complementary. These Q and Q bar are not complementary, so that's why this state is prohibited. So this 0, 0, at this 0, 0 condition, I am getting an invalid output. Okay, so the output is invalid at input 0, 0. Why it is invalid? Because Q and Q bar are identical. That is 1, which is not possible in case of a latch or a flip-flop. So let's proceed to the second case, 0, 1. Okay, so let's check the case of 0, 1. Now I am erasing this. Okay, and check the case of 0, 1. So this is 0, this is 1, and let's assume that this is 0 and this is 1. So this 1 reaches here and this 0 reaches here. Now start the operation. For this 0, 1, I will be getting the output 0, 1, output will be 1. and this for this 1 0 output will be 1. So this one reaches here as 1 and this one reaches here. So this 0 will change to 1. So 0 1 output is 1, 1 1 output is 0. Again this 0 reaches here and this 1 reaches here. So 0 0 output is 1, 1 1 output is 0. I can see that now output had stopped changing. So 1 0 was there and again the next stage is also 1 0. So I can simply state that if I send these feedback again back to the circuit, the state of the circuit is not going to change. So my circuit has stabilized now and I can check that if I assume that my previous output was 0, the next output is 1. So I am simply roughly noting it down that if I assume 0, the next output is 1. So this is Qn and this is Qn plus 1. Okay. So if Qn was 0, Qn plus 1 came out to be 1. Now let's check the second case. If I check the second case, okay. So let's check the second case. When I assume this Q as 1 and then Q bar will be 0. So this 0 will reach there and this one will reach here. So for 0 0, okay, for 0 0 output will be 1 and for this 1 1 output will be 0. I can see that the output has stabilized. Output is stabilized in its just next state only. So if I again send these 1 and 0 outputs back to the circuit, the output is not going to change since it is stabilized. And I can see that Q and Q bar are complementary as well. So these are they are valid also. So if I want to check, if I assume Qn to be 1, the next output is also 1. Okay. If I assume Qn to be 1, the next output is also 1. So I can simply say that the output is permanently 1. If I apply 0 1, the output is going to be 1 in any case, whether the previous output was 0 or previous output was 1. Similarly, if you check this case, you will see that the output is permanently 0. And for the last case, 1 1, you will find that the output is not changing. No change. Okay. If you want to check, we can also check here. So let's also consider this last case where the output is not changing. We can check it. So I am applying 1 here and 1 here and assume it to be 0 and this one to be 1. So this one reaches here and this 0 reaches here. So corresponding to 1 1 output is 0, or corresponding to 1 0 output is 1. So we can see that the output is correct as well because Q and Q bar are complementary, and output is stable as well because 0 1 was the previous output and the next output is again 0 1. So output is stable as well. So I can check that if I assume Qn to be 0, the next output is also 0. Now let's check the second possibility. So for second possibility, we have to assume that the previous output was 1. So if I assume this Q as 1, then Q bar will be 0. This 0 will reach here and this one will reach here. So 1 0 corresponding to 1 0 output will be 1 and corresponding to 1 1 output will be 0. Again we can see that if I assume the previous output to be 1, then the next output is also 1. That means we can see that this Qn and Qn plus 1 both are same. So that's why we are saying that this Qn plus 1, that means next output is not going to change. That means this Qn will be identical to Qn plus 1 will be identical to Qn. So this is the latching operation in which I can latch a 1 by placing 0 1 at the input. I can latch a 0 by placing 1 0 at the input, and if I place 1 1 at the input, then there will be no change in the latched bit. That means whatever bit was latched in the circuit previously, it will be held in its initial stage. Okay, so this is a basic latching operation in which we are trying to latch a bit as per my requirement. Now let's name that latch. Okay, we can see that this complete thing let's write this truth table again. So this is the truth table we have, which we have obtained. 0 0 0 1 1 0 1 1. This was invalid. This was 1. This was 0, and this was QN. No change. Okay. That means here output is set. Here output is reset. Here output is no change. So let's name these A and B as per this set and reset values. So you can see here, if I name them as SR and QN plus 1. Okay. So 0 0 0 1 1 0 1 1, and writing the same table, invalid 1 0 and QN. So you can check here, S is 0, R is 0. That means neither I want to set, neither set nor reset. So ideally, in this condition, output should have not changed. But here it is invalid. Okay. Similarly here, I want to reset. So output should have been zero. Here S is 1. That means output should have been 1. And here both are 1. That means both set and reset simultaneously, which is not possible. Which is not possible. Okay. So if it is not possible, then this should be invalid. So you can check that where I am getting invalid, ideally it should have been no change. Where I am getting no change, ideally it should have been invalid. Where I am getting a 1, ideally it should have been 0. Where I am getting a 0, ideally it should have been 1. So all the entries are swapped here. Okay. So we can see that, we can say that if I replace this table, if I mention this table as S bar R bar and QN plus 1, then this table is working perfectly fine. Okay. That means invalid 1 0 and no change. That means QN. Okay. So this is S bar R bar latch. So this actually, this is AB, this is S bar, and this is R bar. So this is S bar R bar latch, which we have covered previously. But this bar is creating quite a bit of confusion. So if I want to remove these bars, so that normal SR table is ready to me, 0 0 0 1 1 0 1 1. That means for 0 0, if I remove SR, that means neither I want to set nor I want to reset. That means output should not change. Okay. Similarly, for 0 1, I want to reset. I want to reset. That means output should be 0. If I want to set, output should be 1. I want to set, I want to reset. I want to do two things simultaneously, which is not possible. So that's why it will be invalid. Okay. So this is the actual SR latch truth table. But to realize this circuit, we have to make changes in this circuit. So what are these changes? The changes are very simple. So this was the original S bar R bar latch. So this is the S bar R bar latch. Okay. So we have to simply remove these bars. So to remove these bars, I'll be requiring simple NOT gates. if it is getting confused, so I am clubbing them. So now this is S and this is R. That means two extra NOT gates are there, which are being appended at the input side. So this S bar and R bar now is now equivalent to SR. Okay. So for this SR latch, this is the truth table. So this is the SR latch, which is the actual topic of our syllabus, SR latch. So this is the basic SR latch. And how this SR latch is converted into a flip-flop, we just need to include a timing element, which is a clock. So in the same circuit, if I include a clock, so I'm again drawing this circuit. And this time I'm having a clock here. So this becomes the SR flip-flop. So this is the SR flip-flop. So this is the journey of a latch and how a basic cross-coupled inverter then converted into NAND based latch and then converted into AB latch and then converted into S bar R bar latch and then SR latch, and finally we are getting the SR flip-flop by having a clock connection at the input gates. Okay. And the truth table is again identical, same, exactly similar to the SR latch 00011011, and this will be no change, QN 01, and this will be invalid. The same table is valid for SR flip-flop as well. The only thing is this operation is going to be completed only in presence of clock. In case of a latch, there was no foundation of clock. That means you just apply the inputs and you will get the output. But in case of a flip-flop, you need to apply the inputs and then apply a pulse, a square wave pulse. If you are not going to apply a pulse, the circuit is not going to function. That's the only difference between a latch and a flip-flop. That means latches are unclocked and flip-flops are clocked. So in presence of clock only, the circuit is going to work, and in absence of clock, the circuit is not going to function. So this is the basic difference between latch and a flip-flop. Okay. So this is a basic SR flip-flop, and then we have seen that there is an issue with this invalid problem in SR flip-flop. So we will proceed to JK flip-flop now. So again drawing the same SR flip-flop. Okay. So this was the clock connection, and now I am not naming them as SR, S and R. I am naming them as J and K, and these two are additional connections. I am changing the color so that these additional connections to prepare a JK flip-flop are explicitly visible. So now this is a JK flip-flop. We have included two more connections in an SR flip-flop, and this SR flip-flop is acting like a JK flip-flop now. Okay. So now the table for this JK flip-flop is JK QN plus 1 0 0 0 1 1 0 1 1. So first three cases are identical because there was no such issue in them, 0 1, and this time here it will be QN bar instead of invalid. That means toggle. So toggle means in SR flip-flop, I was saying that I want to set as well, I want to reset as well. So I won't be able to do anything. So that's why it was invalid. But in case of JK flip-flop, I'm saying that if I want to set and reset, definitely simultaneously it won't happen. But once I will set and then I will reset. Set, reset, set, reset. That means output will change 1 0 1 0 1 0. That means it will toggle on clock by clock basis. Okay. So this is JK flip-flop.